Have you ever wondered how a website like Amazon or Netflix can handle millions of people all at the same time and just not crash? Well, it's not magic. It's a field called system design. And in this explainer, we're going to build one of those massive, scalable systems right from scratch, starting with the very basics.
Seriously, just picture it. It's a huge sale. Millions of people are clicking, searching, and trying to buy stuff all at once. How on earth does a site like that not just grind to a halt? Well, that is the core problem of system design. And by the end of this, you're going to know exactly how they do it.
Okay, so everything, and I mean everything, starts here. It's the most basic relationship on the internet. Your phone, your laptop, that's the client. It's what asks for things. And somewhere out there, there's a powerful computer, a server, that's just waiting to answer those requests. Pretty simple, right? But how does your client find the right server among literally billions of them?
Well, every single server connected to the internet has a unique address, called an IP address. You can think of it just like a street address for a house. Without it, your browser would have no idea where to send your request. But you can probably spot the problem here. There's no way you're going to remember a string of numbers for every single website you want to visit. It's just not how our brains work.
And this is where the first real piece of our system comes into play, the DNS. The best way to think of it is as the internet's telephone directory. You don't remember your friend's phone number, right? You just look up their name. DNS does exactly that for websites. It takes the name we can remember, like Amazon.com, and finds the IP address that computers understand.
So, here's what happens in that split second. Before your browser even tries to talk to Amazon's server, it makes a super quick call to a DNS server first. It basically asks, hey, where do I find Amazon.com? The DNS server looks it up and replies with the correct IP address. And then, and only then, does your browser know exactly where to go. This whole thing happens in milliseconds, every single time you go to a website.
Okay, so our system is up and running, people are using our app, and everything is going great. Maybe a little too great. All of a sudden, traffic is exploding. Our one single trusty server just can't keep up. It's trying to handle thousands of requests all at once. It's slowing down, and it's right on the verge of crashing completely.
This, right here, is the first huge hurdle every successful website hits. You've got more people coming to your site than your machine can handle. So what's the move? How do you scale up?
You've basically got two options. You can scale vertically, which just means you make your one server bigger and beefier, more power, more memory. Think of it like giving a single cook a much bigger kitchen. Or you can scale horizontally, which means you just add more identical servers. Instead of a bigger kitchen, you're just hiring more cooks. Now, both of these approaches work, but there's one absolutely critical difference.
See, to scale vertically, you have to shut the server down to install all the new parts. For a small app, maybe a few minutes of downtime is no big deal. But for a site like Amazon, a single minute of downtime during a big sale could mean losing millions of dollars. For any major system, downtime just isn't an option, which makes horizontal scaling the only real choice.
Okay, but if you have a whole bunch of servers, how does a new user's request know which one to go to? Well, that's where this thing called a load balancer comes in. It sits right in front of all your servers and acts like a traffic cop. It sees all the incoming requests and cleverly spreads them out, making sure that all the servers are sharing the work evenly.
So let's look at our system now. The user's request still goes to the DNS first, but now instead of getting the IP address of our one server, it gets the address of the load balancer. The load balancer then takes over and passes that request to whichever server is least busy. And just like that, we've built a system that can handle a massive amount of traffic without breaking a sweat.
All right, we've solved the traffic problem, but of course, a new problem pops up. Our application has gotten huge. All the code for everything, user logins, processing orders, handling payments, it's all just tangled up together in one giant code base. This is what we call a monolith. And it's a nightmare because making one tiny change to payments could accidentally break the login system.
The solution is to break it all apart. So instead of one giant application, we create lots of small, independent applications called microservices. Each one has exactly one job. We have a service just for authentication, another one just for orders, and so on. And the best part, if you're suddenly getting slammed with new orders, you can add more servers just for the order service without touching anything else.
So now we've got all these little independent services running around. But how does a request from a user find the right one? That's the job of the API gateway. It acts as the single front door for our entire system. It looks at a request and, kind of like a receptionist, says, you're trying to make a payment. Okay, the payment service is right this way.
So check out the flow now.
The client talks to the API gateway. The gateway figures out where the request needs to go and sends it to the right group of microservices. And notice, each group of microservices can have its own load balancer to spread out the work. We're building in layers of organization and, more importantly, resilience.
Okay, let's think about a new problem. A user clicks buy, and their payment goes through. Awesome. The very next thing you need to do is send them a confirmation email. Now, sending an email can sometimes take a few seconds. So should you force the user to just stare at a loading screen until that email is sent? No way. That's a terrible user experience.
This is a perfect job for a message queue. Instead of dealing with the email right away, the payment service just scribbles a quick note, like a sticky note, that says send confirmation for order 123 and drops it into this queue. The payment service is now totally free to immediately respond to the user and say success. Then, a completely separate process, an email worker, can come along later, pick that note out of the queue, and handle the task in the background.
Now, there are a couple of different ways services can talk to each other like this. A queue is perfect for one-to-one delivery. One message gets picked up by one worker. It's like a to-do list. But what if one event needs to kick off many different actions? That's where a pub-sub model, or publish-subscribe, comes in. The payment service can just publish an event, like a loudspeaker announcement that says payment complete, and multiple services can all hear that announcement and react at the same time.
Our system is now incredibly powerful and super well organized. But we've got one last big problem to solve: speed. Let's say all of our servers are physically located in the US. Well, for a user in India, their request literally has to travel halfway around the world and back again. That delay, what we call latency, makes the whole app feel sluggish and slow.
The solution to this is a Content Delivery Network, or CDN. A CDN is just a huge global network of servers. Its only job is to take your static files, so things like images, videos, big chunks of code, and store copies of them in data centers all around the world. The whole point is to bring your content physically closer to your users.
And the impact is just massive. I mean, look at this. By serving content from a server that's geographically close to the user, you can absolutely slash your page load times. We're talking about going from 2.5 seconds down to less than 1. That's a huge deal for user experience.
So when that user in India requests a product image, instead of their request traveling all the way to the US, it gets picked up by a local edge server from the CDN right there in their region. They get the image almost instantly. This not only makes the site feel faster for them, but it also takes a huge amount of load off of your main application servers. It's a win-win.
So let's just pause for a second and look at what we did. We started with the absolute simplest thing you can have: one client talking to one server. And then, step by step, we solved one problem after another until we built this global, resilient, incredibly fast system that can handle millions of users.
We've designed a system that can handle success. It can handle millions of real users. But what about the fake ones? How do you stop a malicious actor from trying to flood your system with millions of bogus requests to take you down? Well, that's a whole other can of worms, but it is the next crucial question you have to answer in the world of system design. Thanks for watching.